Hello, welcome to this MATLAB video tutorial. Today's lecture is concerned with curve fitting and in particular with the least squares criteria. So let me first introduce the basic concept behind least squares. If we have some data points, as we can see here in the picture with these blue dots, the least squares criteria wants to find a curve here, this degree 1 polynomial, this line, that best fits all these data. Of course, we have so many data points, it's impossible that the line goes through all of them, yeah, as we were doing with pure interpolation. Here, what we want is to minimize the distance of each of the data points to the line. So the distance, which is the difference between the value of the function minus the value of this polynomial, we want to minimize the square of these distances. Okay, that's the least squares criteria. Usually we compute what is called the squared error. This is the sum over all the data points of the squared distance. For example, if px was the pure interpolating polynomial, that would mean that the value of the polynomial at the data point is equal to the value of the function at that point, and that will mean that this error is 0. Okay? If the value of the error is quite small, that means we have a quite good curve fitting. If the value of this error is very big, it means that the curve fitting is not very good. Okay, so normally this curve is a polynomial, but sometimes if we know, for example, that our data points have some kind of periodicity, we can use trigonometric interpolation. Px can be a linear combination of sinus, or maybe other types of curve fitting if we know that our data points have some exponential growth. So in general, we will use polynomial interpolation, but it's important to know it can be other types of interpolants. The simplest case is the linear regression, the case where the polynomial is a degree 1 polynomial. And in this case, what we want to minimize is the sum of the squared errors. And if we minimize, so we want to find the parameters a0 and a1 that minimize this function. So we take the partial derivatives and equal to 0. We will find the resulting system we have to solve to find the values of a0 and a1 is this system that we can simplify and write in matricial form to look like this. Okay, so n plus 1 is the number of data points that we have from 0 to n, that's n plus 1. Then here we have the sum of all the x components of our data points. This is a symmetric matrix. This is the sum of the squared values of the x component of the data points. a0 and a1 are the coefficients we are looking for. And here we have the sum of the y component of the data points, and here x times f of x of our data points. So all this is known, all this is known. The unknowns are the coefficients of our polynomial. So let me show you how we can compute the least square curve fitting for this very simple case, degree 1 in MATLAB. Okay? So if we start MATLAB, first we need to define the working directory. Today I will work in this folder. And I'll start showing you the file main linear regression. This is a very simple code where we will find the line that is the best fit for some given data points. Okay? So first I clear all the workspace variables, close all possible open figures, clear the common window, and I define a function, okay? I will use this function to define my data points. And here I define 15 data points between 0 and 5. Yeah, so if I do that, I can see that XPB are 15 data points equally spaced between 0 and 5. Okay? Then the values of the function at these points are computed and are called YPB. And NPB is the number of points, in this case 15. Okay, so if I do that, we can see that the value is 15. Now I will define matrix A and vector B as we saw in the slides. NPB is the number of data points, and then sum XPB will compute the sum of all the components of this vector. So let me show you. If I call the command sum and I input a vector, the result is the sum of all the components of the vector. So that's what we are doing here. We are computing the sum of all the XPB values. Here we are computing first the squared value of each of the components of XPB. Because of this dot here, we are doing a component-wise square, and then we sum all of the components. Okay, so if I do this, just to show you, let me not use the sum first. Okay, this is just going to compute the squared value of each of the components of the vector. And then we will compute the sum of all the components. Okay? So I will just follow this formula to compute matrix A, and then to compute this vector called B. Okay? So B is the sum of YPB, the images of the function, and the sum of the images of the function times XPB. Okay? We can see here X times YPB. Okay? Now we tell MATLAB to solve the linear system of equations just writing this backlash. Okay? You give the matrix, backlash, and the independent term B, and then A will contain the solution of the linear system. So in this case, the coefficients of our line. Yeah. Now, let's define the drawing points and plot the obtained line. In this case, the line is going to be the first component of this vector A plus the second component of this vector A times x. Okay, so the first component is the constant. As we can see in our slides, we use the first component was the constant term, second component is the x term. So that's what we do here. And we define these x endpoints. These are just points that are used for plotting purposes. Okay, so I define these points and I evaluate the value of the line through these points. Okay, so finally I can compute the squared error, which is the difference between the data points and the value of my line at the data points. Finally, I plot the figures, I plot the data points and the line that I already computed, and to plot the line I use these drawing points. Okay, so let's run the code. And here we can see the result. The dots are the data points and the blue line is our curve fit. And if we show here the vector A, it contains the coefficients of our line. In particular, the first term here is the constant one, plus the second coefficient here is the one that multiplies the x. Okay? So in order to plot the line, we use the interpolation points, x int. In order to understand better what are these plotting points, if instead of using that much, I use a very coarse grid, let's say I just use, I don't know, 1, okay, step of 1, and I do the drawing again, you will see the drawing is not okay because it's a line. Yeah, the drawing is going to be nice because it's just a line. I wanted to explain that these x in are the points where we evaluate the function. If it's a line, of course, you don't see difference between using a lot of points or just 2 points even. Yeah. Okay, I will explain that later better because in this case it's not very easy. So how can I explain that? Okay, I will explain later on. Okay, so this is one example. Now let's move on. Exercise 1. Let's do this first exercise here. Exercise 1 tells us to compute the linear least squares fit for this data. And using this fit, we have to find an approximated value of the function at different points. Okay, so let's do this. I will start copying all this here. Now, instead of a function, now they give us the x values and the y values of the function. Okay, so these are the xpb that we want to use. And these are the values that the function has at those points. NPB is going to be the length of this vector xpb. Okay, then we will define the matrix A, the vector B, solve the linear system of equations, and then we will define the drawing points. Here, the data points go from 0 to 0.5. So let's say we define from 0 to 0.5 using a step of just 0.5, as the drawing is just a line with 2 points is enough. And then we will do the plots. Okay, that's it. Now, using this fit, it says find an approximated value of the function at these points, -1, 0.05, and 0.6. Yeah? Here we are evaluating the line at these points, 0 and 0.5, but we also would like to evaluate at these points. So let's do it. At points, these ones. So for example, at point -1, the value is going to be this times -1, yeah? And if I want to compute its value at 0.05, then x equals 0.05, yeah? And if I want to compute the value of the line at 0.6, then x equals 0.6, yeah? So that's one way we can evaluate the line at any point we want. Another option is to use polyval. If you use polyval, which is a built-in command in MATLAB, you need to give here the coefficients of the polynomial, but remember in MATLAB you use the reverse order. So the first coefficient is the one associated to the maximum degree, and the last one is the constant coefficient, okay? So you need to switch the order, reverse the order of the coefficients, okay? And here you will introduce the points where you want to evaluate the polynomial. That's another option, okay? So for example, we can do this. I will not write this, so we will see on the screen of the command window. Okay, let me run it. Okay, so first we can see y1 is exactly the same as using the polyval, y2 is exactly the same, y3 is exactly the same as using the polyval command. And this is the plot that we obtain. These are the data points, and in blue we have the computed line, okay? So that's what we were expected to do. We have seen these two options are equivalent. We can either compute the value of the line at point -1 using this formula, which is y1, or use this command, polyval, and in just one command you can introduce as many points as you want where you want to evaluate the polynomial, okay? Okay, now we have seen the simplest case, which is a linear regression, but sometimes we want to do a curve fitting with polynomial with a higher degree. So let's see how we can do that. So let's use this file, main list squares. In this file, we will see how to use the Polyfit command to find the best fit in a least square sense, okay? First of all, we clear all the workspace, close all possible figures, clear the command window. Now I define a function. Remember to use the dots, okay, in order to compute with vectors when x is a vector. We define the data points. And then if we use the polyfit command where n is smaller than the number of data points -1, we will find the best fit in a least square sense, the best polynomial of degree n that fits our data points. Of course, in the case where you have, let's say, x, y have only two components, you have only two data points. If you use n equals 1, then in fact, this will return the pure interpolated polynomial because the best fit for a line to minimize the distance to 2 points is the line that goes through those points. Yeah. So polyfit can be used both for least squares fitting, but also it's used, as we saw in the previous video, to find the pure interpolating polynomial. But in that case, you need to use the proper value for n, which is always the number of data points -1. Okay, now in particular for n equals 1, we have the linear fit in the least square sense, but we can use any degree we want. Yeah? If we call polyfit the data points and we write here 2, that means it will compute the parabola that best fits the data points. Now 3 will compute a cubic, 4 a polynomial of degree 4, and so on. This polyfit command will always compute the polynomial best fit, and you introduce here the degree of the polynomial, okay? Then you can evaluate the polynomial on a finer grid just for plotting results. Here we use a very fine grid because we want to plot not only a line, but here we want to plot a parabola, a cubic, polynomial of degree 4, and we use polyval to evaluate the different fits in the drawing points. We could also do it like this, okay? But I think it's easier to use the polyval command. Now we compute the square root error for each of the cases. The square root error when you use a line, the square root error when we use the parabola, and so on. And finally, we plot the figures. Okay? So in these figures, we plot the data points. We plot the fourth curve fitting in the least square sense, degree 1, 2, 3, and 4. And let's see what we get. So basically, the dots are the data points. The green line is the degree 1 polynomial, so a line. Degree 2 is a parabola. It's trying to minimize the distance of these curves to the data points. Yeah? As there are 1, 2, 3, 4, 5 data points, see, when we go up to degree 4, we are in fact computing the pure interpolating polynomial, and we can see here that the square root error is 0. In fact, it's 0. This is in machine precision. Okay, so it's a 0 within machine precision, and that's because we have only 5 data points, and we compute a polynomial of degree 4, and it can go through all the data points, so the error is 0. Okay, now I wanted to explain you another option to compute least squares fitting, and it's using the interactive fitting. We will just plot some data points. So we just need to plot some data points, and then we will go to Tools, Basic Fitting. Okay? Now here we can select if we want to compute the line, the parabola, the cubic that goes through all these data points. If we select Show Equations, we will see all the equations up to 5 digits. Okay, we can also plot the residual information at each point, how much error we have, the distance between the data point and the curve fitting the data. If we click on this arrow, we can find the coefficients of the polynomials up to 5 decimals. And if we click on this arrow, we can enter here a value where we want to evaluate the curve. So for example, if I selected the cubic, I can evaluate this third order polynomial in any point I want, and I can evaluate it, 4.2. Yeah? Then I will know the value of the polynomial at this point. The drawback of using this interactive fitting is that it only gives you 5 significant digits. So if you want more precision in your solution, you can use it, but you need to use this save to workspace. Let's say we don't want the residuals. We will just save to workspace the polynomial coefficients. Okay. Then if we go to the common window, we can see here fit, and we have the coefficients of our polynomial with all the decimals. So here we only had 1, 2, 3, 4, 5 decimals, but here we have the coefficients with all the decimal places precision that MATLAB is computing. Okay, so Just to finish, I wanted to propose you an exercise. The exercise is the following one. Please execute the following commands. Load census, define xpb as the variable cdate and ypb as the variable pop. In fact, what this does is to load some data points from the US population between years 1719 and 1919. And what you need to do is first plot the data points, then compute the linear fit through those data points, and then compute the best fit parabola, okay? But you have to return its coefficients with 8 decimal places, okay? And finally, use these fits, both the linear and the parabola, to predict the population in these different years, okay? And that's it. So, thank you very much. Bye-bye.